Hello, my name is David Castrejon, and today I'll be presenting my research project titled Graph-theoretic Models and Algorithms for Imprecise Probabilities. This project explores reasoning under uncertainty using both Dempster-Shafer theory and Creedal networks. As mentioned in my research paper, the primary sources of this information I'll be referencing are Kozman's papers, one of which is titled Graphical Models for Imprecise Probabilities, and also the content of our coursework and the coursework textbooks and lectures. So my goal with this project was to implement computational models that handle uncertainty in medical diagnosis, and to compare the Dempster-Shafer approach with the interval-based approach of the Creedal networks. And for the purposes of this presentation, I'll walk through the code, explain the methods, and then analyze the output to demonstrate how the implementation handles uncertainty and is propagated through these networks. So first, let's go ahead and let's start with the Dempster-Shafer portion of this project. Okay, so as we can see here, I focused on modeling uncertain evidence in a medical diagnosis scenario using two diseases, being the flu and the cold. And I also modeled their associated symptoms, the fever and cough. So the main objective was to represent uncertain information about the diseases and then propagate this uncertainty to the symptoms. In my code, I defined some mass functions, which assign degrees of belief to sets of possibilities. For example, the mass function for the flu assigns 10% belief that the patient has the flu, 80% that they do not, and 10% for representing some uncertainty or ignorance. I also implemented Dempster's rule of combination, which I will show here. Here we go, which I will show here. And this allows the merging of evidence from different sources. This code also has belief and plausibility functions, which provide some bounds on the probability and allow us to compute some ignorance. So finally, the propagation function, which is shown here. The propagation function allows us to scale the symptom masses according to the belief of the parent disease. According to the belief that the parent disease is present, So this is hierarchical. It is a parent-to-child adjustment, and the results of the code show that the belief in the fever and cough is low, which I can go ahead and demonstrate here. So as we can see here, we can see the initial assignments, and the combined mass, and then also the propagated mass for fever and cough, which utilize these two pieces of conditional evidence here. And we can also see at the bottom the belief and plausibility for the fever and cough. Now, this reflects the original disease evidence, and the plausibility is slightly higher because the code accounts for the uncertainty in the parent diseases. So this output demonstrates that Dempster-Shafer theory allows us to model uncertainty while explicitly representing some ignorance. So next, I will go ahead and look at the Creedal network portion of the code, which is here. Let me make this smaller. Great. So the Creedal network is similar to the Bayesian network. It allows for interval probabilities rather than fixed values, and this means that each node can have a probability range for being in a particular state. And this allows us to represent uncertainty a bit more directly. So for example, the flu might be present with a possibility between, let's say, 5 and 10%. So in this network, I modeled the same medical scenario as I did for the Dempster-Shafer code that I have just shown. And it is modeled in the same way where we have the flu and cold as the root nodes and the fever and cough as the symptoms. Well, modeled similarly, I should say. So each node is represented by a Creedal node object, which stores its name, the parent nodes, the Creedal table that defines these interval probabilities that I just mentioned, and also the network class, which allows us to link parent and children and provide some methods to compute some computations for this network. So it's important to mention that the computations that are included in this network involve extreme point marginal computation. And this is important because in a Creedal network, each parent node has a probability interval rather than being a single value, which means that a child node can have a wide range of possibilities depending on the combination of its parent states. So the extreme point marginal computation solves this issue by considering only the extremes of each parent interval and then enumerating all these combinations of these extremes. And we can see the implementation here. This is also cited from Kozman's 2000 paper. And for propagating through all these extreme combinations, the algorithm is able to find the smallest and largest possible probability for each child node. This guarantees that the resulting intervals are mathematically correct, and also they show all plausible distributions. And this is done in a recursive implementation manner, so it handles the root nodes, and since the marginal intervals are just their defined ranges, it computes each child node by scaling conditional intervals according to the parent extreme probabilities. And there are some advantages to this method. One of them are that it captures all possible outcomes, so it ensures that no plausible probability is unconsidered. However, there are some downsides computationally. So one of which is that the extreme combinations, they grow very rapidly with the number of parents and the size of the network. So that can be very computationally demanding in a large network. For example, with only 2 diseases, let's say, and 2 symptoms like I have done here, the computation is very manageable, but for a large-scale network, this would be rather unsuitable. So let's go ahead and run this code, and then we can analyze the output and compare and contrast it with the Dempster-Shafer output. Okay, so here I have included some debug statements to show a little bit of this computational complexity. This is a rather small network, so it's very tractable. It's very easy to compute at this small scale. However, we can see here that all of these intermediate computations show that, or they can show how, although for a small network, it still does a lot of operations. And then for a large scale network, this could be untractable. But we can see the results down here. And now we can go ahead and analyze the results. So after running this Cradle network code, we can see that the flu is present with the probability between 0.05 and 0.10. The cold is also present, and it's between 0.10 and 0.2. And these intervals are taken directly from the Cradle tables, and they show that the root nodes return their specified ranges exactly. So for the child nodes, the fever is present as well, with a probability between 0 and 0.16. And all of this shows that the upper bounds reflect a more optimistic combination of the parent states, where both diseases are present and the conditional probability of the symptom is at its maximum. So my first observation, or another observation here that I should say, is that the fever has a wider range than the cough, showing that it's more sensitive to combinations of the parent states. And also another thing that I noticed here is that the increase of parent assignments in the debug output shows that the nature of this computation is heavy, and this could have some performance issues for larger networks. So let's go ahead and compare and contrast these results with the Dempster-Shafer results to get a nice comparison between the two, showing how they differently handle reasoning under uncertainty. So it's important to note that the Dempster-Shafer model used in this project, it uses a basic probability assignment. It uses a basic probability assignment that are point valued, where in contrast, the Cradle network, as we can see, it represents interval probabilities in the network parameters. But however, the Dempster-Shafer inference also provides somewhat of a interval valued results via the belief and plausibility measures. And this provide lower and upper bounds for each event's probability. This also shows that the frameworks both yield interval valued uncertainty at the inference level, and that the source and the interpretation of these intervals differ substantially, however. So for the Cradle networks, they encode imprecision within the model itself, while the Dempster-Shafer approach expresses imprecision through these belief and plausibility calculations after the evidence combination. So comparing these two results, we can see how these frameworks handle uncertainty. In the case of Dempster-Shafer theory, belief and plausibility intervals incorporate partial support and conflict, while the Cradle networks provide a guaranteed probability bound that encompass all the distributions consistent with the specified intervals. Also, the magnitude and symmetry of the intervals differ between the frameworks too. So in this network, the Dempster-Shafer interval for child nodes remain narrow, likely due to low residual ignorance. And this also shows a minimal conflict in the available evidence as well. I should probably scroll up to show. But meanwhile, the Cradle networks are a bit more mathematically tight, and the lower bounds can also reach zero, reflecting a full range of uncertainty as well. The propagation behavior also varies too. So in the Dempster-Shafer theory approach, it can sometimes produce counterintuitive interval widths due to some conflicting evidence, whereas the Cradle networks, they yield a bit more rigorous marginal bounds. So these differences, they have some consequences, and Dempster-Shafer theory seems a bit more useful for analyzing evidence aggregation and conflict resolution, whereas the Cradle networks seem better suited for reasoning under partial knowledge, and they offer precise bounds that support the worst case and best case decision making. So computationally, these frameworks also both face challenges. The Dempster-Shafer propagation also becomes expensive as the frame of discernment grows, especially when you have multiply connected networks where evidence has to propagate across multiple paths. And this can lead to some repeated calculations and normalization. The Cradle network also faces some complexity as well when enumerating a large network, especially with extreme points. However, the Cradle network can use some optimization techniques like convex optimization, and it can exploit the network sparsity, so that can scale more effectively than the Dempster-Shafer theory approach in some contexts. But both frameworks, they show a trade-off in reasoning under uncertainty, where Dempster-Shafer emphasizes interpretability and conflict management, whereas the Cradle networks provide more generality and bounds at the cost of some increased computational complexity. But together, they do illustrate a framework for reasoning under uncertainty, from the belief function propagation to some interval-based probabilistic reasoning. And this highlights that they have some complementary strengths when it comes to reasoning under uncertainty. And just to drive this point home, I will, because we've been looking at code for a little bit, I will also show some of the figures that I have mentioned in my paper. And as we can see here, the Dempster-Shafer approach incorporates this point-based approach, where the Cradle network has the interval-based approach. But yes, these two approaches demonstrate some trade-offs, but together they provide a great framework for reasoning under uncertainty. And this is the conclusion of my presentation from a research project this semester, demonstrating an implementation of two graphical models, one being based on Dempster-Shafer theory, one based off Cradle networks, for medical diagnosis and representing imprecise probabilities. So thank you very much for listening, and that is all.